Hello, and welcome to Linear Algebra. This is lecture 37, Characteristic Polynomial. Last time, we talked about how to go about computing determinants. This time, what we want to talk about is how are determinants and eigenvalues related. Okay, so part of the answer is immediate from some of the things we did last time. Namely, if you have an n by n matrix with coefficients in the field f, then we know that lambda in the field is an eigenvalue of A if and only if the kernel of A minus lambda times the identity is not just the zero vector, which is the same as saying that A minus lambda times the identity is singular, right? Not invertible. And from last time, we know that that's the same as saying that the determinant of A minus lambda times the identity is equal to 0. Okay, so this determinant gets a name. It is a polynomial in lambda. We'll denote it P sub A of lambda. And it is called the characteristic polynomial of A. Okay, so here is an easy fact. If you have an n by n matrix, then the characteristic polynomial of any matrix has degree n. And the leading term is minus lambda to the n. Okay, in particular, leading coefficient is always non-zero. Okay, so let's prove this. Let's let B be the matrix A minus lambda times the identity. So the characteristic polynomial is the determinant of B. And from our discussion last time, we know that we can write that as a sum over all of the permutations of Sn in Sn. Where we put the sign of the permutation, and then we multiply the product of lots of entries of B, n different entries, right? Where we're choosing them using this permutation. Now, for a given sigma and Sn, okay, so if we're looking at one of these terms, and we're interested in the characteristic polynomial as a polynomial in lambda, then we want to know how many lambdas are showing up here. Right now, the lambdas are on the diagonal of this matrix, so we want to know how many of these terms are coming from the diagonal. So let's let f sub sigma be the subset of the numbers from 1 to n that are fixed by sigma. Right. So what I mean is that f sigma is equal to all of those i's such that sigma of I is equal to I. Then this product b1 sigma 1 through bn sigma n is equal to product when I is in f sigma of ai minus lambda, and the product of those i's that are not in f sigma of ai sigma I. Thus, each term in the sum computing the determinant of b is a polynomial in lambda of degree equal to the number of elements in f sigma. The highest possible degree is n, which corresponds to when f sigma has n elements. But if f sigma has n elements, then the permutation fixes all of the elements between 1 and n. So that means that sigma is equal to the identity permutation. And for this one, this term, b1 sigma 1 through bn sigma n, would be the product, I goes from 1 to n of ai minus lambda, which we can write as minus lambda to the n plus lower order terms. Right, and so we've found that we do indeed have a polynomial of degree n, and the leading term is minus lambda to the n. Right, as expected. Okay. Now, if you have a matrix with n distinct eigenvalues, then the characteristic polynomial is going to be the product, j goes from 1 to n, of lambda j minus, right, so let's use variable x, just so it's not confusing which are the eigenvalues, which is the variable. So let's use x for the polynomial variable, and lambda j's are the eigenvalues. So the polynomial you get is going to be exactly this one. Here it is factored into linear factors, 1 per eigenvalue. So how do we know that? Well, it is divisible by x minus lambda j for each j. Right, because we know that the eigenvalues are the roots of this polynomial. So each lambda j is a root, and that's equivalent to knowing that the monomial x minus lambda j divides the polynomial. And because it's divisible by each of these lambda j's, it is divisible by their product, and it's divisible by the product if I multiply by plus or minus 1 as well. So I know that this right-hand side divides the characteristic polynomial. And since these polynomials have the same degree, right? They're both polynomials of degree n. And the same leading term, right? They're both minus x to the n plus lower order terms. They must be equal. Right, so any matrix that has n distinct eigenvalues must have characteristic polynomial equal to this product. Okay, now when we talk about eigenvalues, right, you'll recall that we have a much better theory if the field is algebraically closed, right? Then we're guaranteed to have eigenvalues. So one thing we've talked about before is that every field is contained in an algebraically closed field. Right, so for example, the real numbers are contained in the complex numbers. Call the algebraically closed field K. And of course, we want it to be contained not just as a set, but as a subfield, right? So with the same operations. So again, this is just like the real numbers and the complex numbers. If I have two real numbers and I add them, it doesn't matter whether I'm thinking of them as real numbers or as complex numbers, I get the same result. And same thing when I multiply them. The advantage when we're talking about the characteristic polynomial of working with an algebraically closed field is that the characteristic polynomial factors into linear factors, to linear terms. Right, so over the complex numbers, every polynomial has complete factorization into linear terms, right? And over any algebraically closed field. So our perennial example, if you're looking at the matrix corresponding to rotation by 90 degrees, then the characteristic polynomial would be x squared plus 1. This has no roots in the real numbers, but it factors into x plus I times x minus I in the complex numbers. Okay. So when you're working over an algebraically closed field, and you know that the characteristic polynomial is going to factor, you can talk about the multiplicity of an eigenvalue. Which is going to be just how many times does the linear factor corresponding to that eigenvalue occur in the factorization of the characteristic polynomial. So here's the definition. If f, let f be an algebraically closed field, A an n by n matrix with coefficients in the field, and let lambda 1 through lambda k be the distinct eigenvalues of A, if the characteristic polynomial of A factors as, so I can write it as -1 to the n times x minus lambda 1 raised to some power, call it m1, and then x minus lambda 2 raised to m2, and so on until you get to x minus lambda k raised to the mk. Then we refer to m sub j as the algebraic multiplicity of lambda j as an eigenvalue of A. Okay, so because this is a polynomial of degree n, we know that these powers have to add up to n. So the sum of the algebraic multiplicities is exactly n, right? So when you're looking at an n by n matrix, right, it has at most n distinct eigenvalues. And when you have k distinct eigenvalues, then each one of those comes with a multiplicity, and the sum of the multiplicities gives you n. Okay, so for example, if you're looking at the polynomial p of x, say x to the 6th minus 5x to the 5th plus 6x to the 4th plus 4x cubed minus x squared, then this factor says x squared times x plus 1 times x minus 2 cubed. So this polynomial has 3 distinct roots, but 6 roots if we count them with multiplicity. Right, in which case you could think of the roots as being 0, 0, minus 1, 2, 2, 2. Right, so you have, it's a polynomial of degree 6, so it should have 6 roots, right? And it does if you count them with multiplicity. Okay, now one thing we proved last time was that the determinant, actually we proved this two lectures ago, the determinant is an invariant of a matrix, right? So if you have two similar matrices, they have the same determinant. So it follows that the characteristic polynomial of A, the eigenvalues of A, and their multiplicities are all invariants of A. Okay, so one thing we've gained is we now have more invariants of A, more ways of distinguishing matrices, whether or not they are similar. Okay. Now, if F is algebraically closed, well, if F is algebraically closed, then we know that any A is similar to an upper triangular matrix. And so any invariant you can compute using an upper triangular matrix. Moreover, the elements on the diagonal are precisely the eigenvalues of A counted with multiplicity. All right, that's easy to see because we know that the determinant of an upper triangular matrix is just the product of the elements on the diagonal. So the characteristic polynomial of an upper triangular matrix would just be the product of aii minus lambda when I goes from 1 to n. So in particular, we can see that the trace of A is just the sum of the eigenvalues counted with multiplicity. And the determinant of A would be the product of the eigenvalues counted with multiplicity, repeated with multiplicity. Okay, in particular, the coefficient of x to the n minus 1 in the characteristic polynomial is minus 1 to the n minus 1 times the trace of A. And the coefficient of x to the 0 in piece of A of x is the determinant of A. Okay, so if f is algebraically closed, you can put the matrix into upper triangular form and then compute the characteristic polynomial. And this is immediate to see. But in fact, this is true over any field f. That's because if you give me a matrix, say we're working with real numbers, you give me a matrix of the real numbers, then what I can do is I can compute the characteristic polynomial thinking of it as a real matrix or thinking of it as a complex matrix, and I get the same polynomial. It's because the reals are a subfield, so all of the operations between complex numbers, if you restrict to real numbers, gives you the same operation with the real numbers. So when I compute the determinant of matrix with real coefficients, it doesn't matter whether I'm working over the real numbers or the complex numbers. On the other hand, if I work over the complex numbers, I can replace it with an upper triangular matrix with the same characteristic polynomial and determinant and trace and so on. And I compute the characteristic polynomial from the upper triangular matrix, and then I can see that the coefficients satisfy these identities, right? But then since the characteristic polynomial and the trace and the determinant are the same, thinking of that upper triangular matrix or the original matrix with real entries, I get the same identities working entirely over the real numbers, right? So if you like, the identity holds in the real numbers, whereas this proof of it goes through the complex numbers, right? And in general, this is true for any field. The proof, this proof would go through an algebraically closed field containing it as a subfield. Okay, very good. So to finish off today's lecture, I want to prove a very nice theorem due to Cayley and Hamilton. We've come across Arthur Cayley before. He's the one who started the mathematical theory of matrices. And Hamilton, this is William Rowan Hamilton, who's famous for discovering the quaternions. And this says, if you have an n by n matrix, and you take the characteristic polynomial of your matrix, and then you replace the variable with A itself, you get 0. Okay, so we've talked about evaluating polynomial, or in fact the power series, in a matrix, right? So you just formally replace all of the instances of your variable in the polynomial with the matrix. So this expression makes good sense. I give you a characteristic polynomial, it's just a polynomial. So you can plug in the matrix A and evaluate. This 0 is the matrix 0, n by n matrix 0. So you might be tempted, but it would unfortunately not be correct. You cannot just plug in A into the expression in terms of the determinant of A minus X times the identity. Right, so it's not as easy as plugging A in here and then saying, well, I'm taking the determinant of A minus A and getting 0. I mean, notice, for example, that this would give us the number 0, and here we're claiming that you get the matrix 0. So right there, you can see that, well, something is going off if you try to just plug in the matrix A like that. That is, so if you plug in A instead of X in this expression, that is not the same as plugging in A into X as a polynomial, right? And there are exercises in the book where you can work out more examples of this reasoning not working. So instead, what we're going to do, we'll show that PA evaluated A applied to any vector V is equal to the vector 0 for all vectors V in Fn. Okay, so we may as well assume that F is an algebraically closed field. As otherwise, we can pass to a larger algebraically closed field K. Right, and the point is that the characteristic polynomial doesn't care what field you're using as long as the matrix has coefficients in that field. And then this expression, if it's 0 as a complex matrix, it's also 0 as a real matrix. So showing that this is equal to 0 in the algebraically closed field guarantees that it's 0 in as a matrix with coefficients in the smaller field. So we may as well assume that we're working with an algebraically closed field. Okay, so next, let's note that we can replace A with a similar matrix. It won't make any difference. If A and B are similar, then piece of A is equal to 0 if and only if piece of B is equal to 0. Right, so why is that? Well, on the one hand, we know that piece of A of X is equal to piece of B of X, right? Similar matrices have the same characteristic polynomial. And if B is equal to S inverse, then PA applied to B would be PA applied to S inverse, right? As we've seen before, when you apply a matrix to, when you raise, say, S inverse to a power, say to the kth power, then you get lots of S inverse times S sandwiched in between other factors, and those are all equal to the identity. So you end up with S8 to the K S inverse. But since that's true every time you raise this to a power, then the whole polynomial behaves that way. So S inverse plugged into a polynomial is equal to S times A plugged into that polynomial times S inverse. So in particular, if PA of A is equal to 0, then PA of B is equal to 0, but that's the same since PA is the same as PB, as PB of B equal to 0. Okay, so where does that get us? Well, since we're working over an algebraically closed field and we're allowed to pass two similar matrices, it's enough to show that P sub A of A is equal to 0 for A upper triangular. Okay, so in this case, P sub A of X is equal to A11 minus X through ANN minus X. And correspondingly, P sub A of A would be A11 times the identity minus A through ANN times the identity minus A. Okay. So notice that if you do AJJ times the identity minus the matrix A, okay, so A is upper triangular, right? And in the jth column, it has the jth column looks like entry, entry, entry up to AJJ and then zeros, right? So if I subtract AJJ on the diagonal, then what I have is something, something, something above the diagonal, then a 0 on the diagonal, and zeros all the way down after that. So if we apply this to EJ, so I'm only looking at the jth column, then because we've killed everything from the diagonal down, this is in the span of E1 through EJ minus 1 for all j. In fact, let me point out explicitly A11 times A minus A. If you plug in E1, you get 0, right? Because the first column of this matrix is 0 because it was upper triangular, and then we made the first entry 0. Okay, so similarly, if I do A11 times the identity minus A, and then A22 times the identity minus A, then this kills A11, E1, and it kills E2. So why is that? Okay, well, this matrix and this matrix commute, right? Because A commutes with itself and all matrices commute with the identity. So when I'm evaluating on E1, I could put this factor in the first slot so that it hits E11 first. And then that gives me 0. And then once I have the 0 vector, I'm done, right? So this is true. Now, what about this one? Well, when this factor hits E2, right, as we said here, that's guaranteed to be in the span of E1, right? So this, I don't know what it is, but it's some multiple of E1. But this kills all multiples of E1. So this is equal to 0. And inductively, if you do the product up through AJJ minus the identity, then when you evaluate on EK, you get 0 for all k's from 1 through j. Right, in particular, P sub A of A applied to EK, well, this is a P sub A of A, which is A11 identity minus A product through ANN identity minus A. This vanishes on all of the vectors from E1 through En. right? And since that forms a basis, we see that this matrix must be identically the zero matrix. Okay, so wonderful. That's the Cayley-Hamilton theorem. It's a very cute theorem. Here's one easy consequence. If A is an n by n matrix that is invertible, then the inverse matrix can be written as a polynomial in A of degree at most n minus 1. Right, so for example, let's say you have the matrix 2, 7, 0, 3. Right? In this case, the characteristic polynomial, right, would be 2 minus x times 3 minus x, which if you write out is 6 minus 5x plus x squared. Now the Cayley-Hamilton theorem tells us that P sub A of A is equal to the matrix 0, right, which is the same as saying that A squared minus 5A plus 6 times the identity is equal to 0. Okay, but then what you can do is put the constant factor on one side and the factors with A on the other side. Now I'm going to factor out an A on this side. And then I'm going to divide both sides by minus 1/6. Okay, and now notice what we have here. We have A times some matrix is equal to the identity, right? Well, that means that this matrix has to be the inverse of A. Here I should have put 5 times the identity here. Okay, so, but of course, this same trick of taking this polynomial, putting the constant term on one side, right? Remember the coefficient of the constant term is the determinant. So being invertible, we're guaranteed that you have a non-zero multiple of the identity here. Factoring out an A and then dividing by minus the determinant gives us the inverse as a polynomial of degree at most n minus 1. Okay, and we'll stop there and pick it up from there next time.